In this problem, we're looking at a pendulum that a bullet is fired into the pendulum at 1,000 feet per second. Okay, it sticks in there, and then the pendulum swings up around A. Okay, so what we're going to do here is we're going to recognize that if I take the system as a whole, that would be both the bullet and the block. Okay, the impulse is going to be internal to that system. Okay, the only external forces then are what's going on here at A, because we can neglect gravity. It's going to be small compared to the impulse going on here. So what I can do is I can conserve momentum about point A, because the only impulse about point A is internal to my system. For that matter, G's are essentially lined up with A as well. So momentum is going to be conserved about point A. So initially the only momentum is the bullet, which is RMV. So R is 2.5. We'll get to that in a second. But it's basically R times mv, which is the angular momentum of the bullet about point A. And then afterwards, I'm going to find the moment of inertia of the entire thing about point A times omega 2, which is omega what I'm looking for. So first, let's find the moment of inertia about A of all of this stuff, which consists of the rod, the block, and the bullet. So the rod, okay, this is the parallel axis theorem of a rod. It's going to be 1/12 ml squared, about the centroid, plus md squared, where d is the distance between A and 1. Now I could have just used 1/3 ml squared rather than this combination, but there you have it. Okay. Now for the block here, this is the moment of inertia about its centroid, 1/12 m, and then it's A squared plus B squared. Okay, plus md squared, where m is given there, d is 2.5, the distance between the centroid of this and point A. So that is the moment of inertia of the block, and then this is the moment of inertia of the bullet, which is just the moment of the mass times the distance away. So essentially, there's no moment of inertia about G. There is just the moment of inertia of the particle. So it's md squared. So the d squared is 2.5. Okay, and then m is obviously that. So the total moment of inertia of the rod plus the block plus the bullet is 2.24 slug feet squared. Okay, so I take that, plug it into the top equation. That gives me the right side of the equation. The left side of the equation is, again, before the impulse, it's just the momentum of the bullet, which is the mass of the bullet times its velocity times its distance away from A. So again, we're talking about angular momentum about point A. So it's RMV, where R is 2.5, M is 0.2 divided by 32.2, and V is 1,000. So again, the only thing I know in this equation is omega, and that is 6.94 radians per second. So again, in a problem like this, momentum is conserved about point A for the whole system, because again, that impulse is internal to the system. And when doing that, just recognize that you have this mv, that's a distance r away, that I need to take into account. That's my initial momentum, right? R times mv. Okay, and then that equals the total momentum moment of inertia about A times omega finally.